Hey everyone, Jason here. So a lot has happened since the last video. In the last video, we looked at the filtration system and the dashboard and did walk through a little bit of the functionality of that. So in this video, I'm happy to share that I've got the system completely built out now. And so I want to walk through that and then show you the updates that I've made to the dashboard as well, and how I've really locked in some of the sensors. Because now after this video, we'll be totally ready to brew our first batch of beer on the system. So with that, let's get into it. Okay, so first I want to show the completed system and the updates that I've made. So last video, we really focused on the filtration system that you see at the top there and how it provides the filtered water to the system for brewing. So in this update, what I'm really going to focus on is the rest of it, which is the recirculation system that you can see here in the kettle, and then how that eventually goes out into the fermenter when it's done. So real quick, first on the kettle here, I was able to successfully tap into their system to directly control the heating element, as well as tap into the temperature sensor that was in there. So now I can completely control the heating element with my system. And you can see here that it is plugged into our high voltage box here on the bottom. So I'll be using that to turn the heating element on and off to maintain the temperature. And then the wire at the bottom there is for the temperature sensor, which is going back into the low voltage box here. So what this is going to enable me to do is to monitor the temperature and then set the specific temperature that I want to mash the grains to get the sugar out of the grains. So was able to successfully do that. That was kind of the first big step. And the second step was doing the recirculation system, which is all the hoses that you see here. So first of all, coming out of the kettle, I just installed a simple kind of three-way valve here. That'll be used mainly for taking samples as the brewing process goes along, and then also ensuring that the system gets totally drained at the end, and that there's no beer left in the tubes at the end. So after that, it's going to a three-way valve here. This is the same three-way valve that I used on the filtration system. So very simple. At default, when the system's off, it goes up through to recirculate, and then once the whole process is done and it's time to ferment, this valve switches and then it goes out the other path, and that simply goes all the way up here to that end of the hose, which has a valve on it, and that will be plugged into the top of the fermenter here, so that it can go into the fermenter when it's ready. Okay, so while it's recirculating, let's get back into the actual brewing. So while it's brewing, while it's mashing, I'm going to recirculate the fluid, and that basically increases the efficiency of extracting the sugars out of the grain. So it's going through this stainless steel tube here, and I'll explain what that is in a second. But it's pretty simple. You can see the pump down here, simple 12-volt pump doing the pumping up here and all the way around back into the top of the kettle again. So that's going to be the recirculation path, and I want to spend some time on this. What this is, it's a way to measure the specific gravity of the system. If you're familiar with brewing or not, what you want to do is watch the specific gravity of the fluid, and that's how you know how much sugar is in the fluid, because the specific gravity changes over time as more sugar gets extracted into the fluid. And that's important because the yeast needs the sugar to actually turn it into beer to create alcohol. So that's what you're measuring while you're doing the mashing, is how much sugar is in the fluid, and you do that by watching specific gravity of the fluid while you mash. So what this thing does is it actually is sending vibrations. So there's two piezo sensors, buzzer. One's a buzzer and one's a sensor. So what this does is the one that's closer, that you can see there really well, when the system's on, that one is actually vibrating, and it's what my software is doing is it's sweeping frequencies of the vibrations to find the natural frequency of the system. The other sensor, which is the same thing but behind the tube, that one is sensing vibrations. And what the system does is, as it's sweeping through frequencies, the sensor in the back is measuring the amplitude of the vibration. And what the system does is when it detects what the maximum amplitude of the vibration, it will associate that with a specific frequency that it's hitting during the sweep. And what that does is it identifies the natural frequency of the system. And that's important because as the specific gravity of the fluid changes, the natural frequency of that system should actually change as well. So the frequency that's creating the max amplitude will actually shift. And with the system like this, you can actually measure that shift, and then you can correlate that to specific gravities. So as we do the first batch here, I'll be manually measuring specific gravity and then watching how the natural frequency shifts. And ideally, I can come up with a curve that tells my software, hey, this is when you should have achieved a certain specific gravity, so that it knows the mashing process is done. So a little bit complicated there, and we'll see how it goes in the first batch. But overall, that is now the completed system from the control panels here to the hardware here. So what I want to do next is show the system in operation. I want to turn the heater on and the pump on, show you how the recirculation system works. I want to show you how I've kind of revised the dashboard as well, because I've made some key changes there. So that's what we'll do next. Okay, so here we are inside, and this is the dashboard. And I want to run through a couple of quick updates on how I've changed this, and then we're going to get into the system operation. So the first thing to highlight here is I've decided to make a change in how I'm controlling this system. I'm going to split this into two different applications. So what you see here is going to remain as the dashboard, and this app is going to focus more on the live control of the system. So this is going to be what I'm using when I'm actually brewing beer. And so it's going to control things like on off. It's going to show me live data streams so I can see how the process is going. And then what I'm going to do is I'm going to move all of the analysis and planning part to a different application that I can run at a different time. And what that's going to do is, first, it's going to streamline this, and it's not going to complicate it or clutter it with extra code and extra things that I really don't need to see while I'm brewing. I can't have my app crash because a graph isn't showing correctly, and then it takes down my whole process. So I've stripped all that out, and what I'm going to do with that app is it's going to turn into a recipe app and an analysis app. So as I log the data from the live app is still going to record data and log it to the database. And then later, the analysis app is going to pull that data, and what it's going to do is I'm going to use that as kind of a headquarters to design my beer recipes. And then that system is going to be able to pull in the data and see how the beer brewing process went. And I'm going to add in some extra notes on it, like, taste and some of those things, clarity, color, final alcohol content, all that stuff. We're going to load all that into the other app. And then that app is essentially what it's going to do is it's going to track my recipe progress. So I'll start with a baseline recipe, and then it will pull in the data of the brewing session and my final notes. And then it's going to optimize the recipe and the process for the next batch. And I'm going to plug AI into that system as well. So AI will be able to run through the entire database, the entire history of the brewing sessions for that recipe, and then take in the feedback, optimize it, and then update the recipe so that my live app can then use that updated process and recipe and create a better version. So that's how I'm going to link in the AI optimization. And splitting the apps like that is going to make it really easy to do that. So I haven't built out that other app yet. I'm focusing on the actual controls and brewing the beer first and getting the data, and then I'm going to do that other part next, or later. So now what I want to focus on is this revised dashboard that you see here. So what I've done is I've just really focused on, these are the live elements. So you've got circuit control, that was similar to what it was, but now I've put in a couple of key things here. So we've got a target temperature. This is where I'm setting the mash temperature So for example, if I wanted at like 152 or 155 degrees Fahrenheit, a typical mashing temperature for beer, I'll put that in here and then hit the set button. So what that would look like is 155 set. Okay, so now my system is showing that it's correctly updated to the set point temperature. A couple other things I've added in here. I've added in temperature sensor. So now this is going to read, turn this on. This is going to read what the actual, the temperature of the water or the mash. So that's, you can see now it's showing me what the actual reading of the fluid is. And that's going to be important, number one, to see, but then also for the system to lock in at the specific temperature that I need. This right here, 0%, that's essentially the duty cycle of the heating element. So as it starts, it's going to be 100% on all the time. And then as it slowly approaches the set point, it's going to start to reduce. Similar to like how your oven works. You set a temperature, you turn it on, the oven heats up, and then gradually it just maintains that cooking temperature that you want. So that's what I'm doing here. For those that are a little more technical, I'm using a PID control scheme and control code, proportional integral derivative, to do that. For those that aren't as complicated or technical, you can just think of it like an oven. So that's the functionality here. So what I'm going to do is, one more thing, the specific gravity system. So when this turns on, it's going to start doing the sweeps, and you'll see that. I'm going to take us back out in a second and watch the system. But turn this on. This is going to do the sweeps, and then it's going to start reporting the natural frequency, the frequency with the highest amplitude response, and that's what you'll see here. And this all gets logged over time. So just before, so I don't forget, I'm actually going to write this in with just a dummy test session here so that it starts logging this data. And then what I'm going to do, so we're at 155. I'll turn this on. So what I'm also going to do is I'm not going to turn the pump on at first because that slows down the heating process. I'm going to let it heat up first. And actually another thing I'm going to do is I'm going to take this down to about 75 so that it's just faster so we can see the system response. But I'm not going to turn the pump on. I turn the pump on as it gets closer to the actual target so that it gives the system a chance just to heat up that total volume of water or liquid. And then once it gets close, I turn the pump to start circulating the system, and then that's going to heat up the other components of the system. It's just faster to do it that way. So that's what I'm going to do. We'll turn this on. That's going to start the sweeps, and it's going to start reporting the frequencies here in a second. The reason there's a delay is because it's taking an average, and it takes some time to actually do the frequency sweeps. So it takes about roughly 10 seconds to sweep through the entire range of frequencies. And then what it's doing is it's sampling, it's taking 10 samples and averaging them. And what that does is it smooths out the curve to make it easier to track. You're not taking into account all the little variations. You're kind of focusing on the average, which is what you really care about, and then seeing how that average shifts over time. So what you'll see is it's starting at 0, so it's going to take a little bit for that to ramp up to the actual natural frequency. So we'll just continue to check on that as we go. Similar with the temperature, but the temperature is sampling much faster because it doesn't have to sweep. It's just microseconds every time the code runs through its loop. It's taking a new sample, so that's updating much faster, which is why that's updating almost instantaneously versus this one where it's going to take some time. So okay, now we've got our set point. So the heating element has really 3 functions: on, off, or auto. So on is just full on, doesn't need the temperature, and that's when I'm going to bring it up to a boil. So when it's boiling, I just want it full on. I don't care about temperature. That'll be just on. Off, obviously off, and then auto is going to be the auto mode to maintain the temperature. So what I'm going to do is I'm going to go ahead and start this. You're going to see the system activates 100%. And it is, the high voltage is fully on here, 12 amps at about 120 volts. That's what I would expect, and that's what the heating element is rated for. Roughly 1600 watts is what it's rated for, but obviously we're a little bit under the specs of voltage and current. So, and that's really just because of the house voltage supply and the way that it runs through the system. There's some natural losses in the system. So it's running a little bit lower, but that's not a huge concern. It's still going to do the job. So what we'll see is that this temperature is going to start to slowly approach 75. Then it's going to start to drop the cycling, or it's going to start cycling lower from 100% down to, you know, something that just stabilizes the temperature. And then as we get really close, I'm going to turn the pump on, and that's going to kind of start heating everything else up and really preparing for mashing. I'm not going to mash today. This is just an example. So in a real mash, I would put this at a much higher temperature to prepare for that, and you know, everything would adjust accordingly. So real quick, while we're waiting for that, what I want to do is I'm going to bring this over and show you what's happening on the back end of the system. Another thing that I've changed is I have updated the kind of the architecture and the schematics of how the system works. In the past, I was just broadcasting data from the hardware out in the garage. So it wasn't really sophisticated. It was just basically every second it was blasting out data. And the issue I was having with that is that sometimes the messages would get confused. If you're sending a command at the same time that the data is going over the same line, they get confused and the data doesn't show up, and then you start getting errors in your system and the communication gets all thrown off and commands get missed. You can think of it like you're in a noisy room, you're trying to have a conversation with someone, and you know, if two people are saying things at the same time, you're not going to be able to understand what was said or comprehend it. So that's kind of what's going on here. So what I did was I changed it. So now my front end dictates the communication protocol. So what's happening is, essentially what happens is that the front end now will send a command to the hardware. It'll basically say, hey, send me your data. The hardware now sends the data. So there's no chance that there could be miscommunication because the front end is also queuing commands. So it'll only do one at a time. If there's a command in the queue, it'll send the command, wait for the response. Then it will send the other one to say, send me your data. So it's just it's basically a, you know, pretty basic handshake protocol where, you know, you're asking, receiving. There's no conflict there. So that's one of the things that I've updated that's really helped the robustness of the system. So now you can see we've recovered here. So what you're actually seeing here are a couple of things. The kind of the big data that you see there with a lot of commas and colons, that's the data package from the hardware. It's in a JSON format, kind of like a database format, or like what you'd see in an Excel file. You can think of it that way if you're not as technical, but it's essentially key value pairs. So you're saying, you know, for these first one, these are all the circuit statuses. So, you know, the 10 different circuits, is it on or off? And you can see most are zeros, some are ones. That means it's on. And then you can see later there you get into some of the actual data. So the high voltage, you know, you can start to see the volts, amps, and power, and that's what's showing up on the dashboard, as well as like specific gravity, target temperature, or temp F is the actual reading. Target temp is the target temp set point. So that's what's going on in the background, and then any kind of commands that are sent and received, that's showing up as well. So that's what's happening in the background of the system. It's, you know, being sent back and forth, and what you see here is the result of that. So okay, so now what you can see is that we've kind of dialed into our frequency. This is what is to be expected from the system, around 6,400 hertz. That's what I've estimated the natural frequency of the system should be without anything else going on. So just the natural frequency of the discs of the stainless steel tube itself, it should be right around there, and that's where it is. And now you can see the duty cycle, and it's starting to cycle on and off because we're getting closer to that 75-degree temperature. And this did take quite a bit of correlation to get the right amount of response. You don't want something too aggressive, you know, because then what ends up happening is it overshoots, especially with something like water, because it takes time for that water to actually heat up, and then for that to actually show up on your thermometer. It takes time for that to happen. So you don't want to like blast it with power and then cut it off at the very end, because what's going to happen is that that water is going to continue to heat up and heat up until your system recognizes it, and you're actually going to overshoot, so you're going to be higher than what you want it to be. So you got to start cycling it before you get it there, and then kind of gradually, approach it. Again, similar to like what your oven does, and the PID control is really really great at doing that. It's very commonly used. So that's what's going on here. So we're getting pretty close here. We still got about 10 degrees to go, so it's still got some time. I think what I'll do is I'll just wait. We'll fast forward this part, and then once it gets close, then I'll turn the pump on and we'll go out and look at the system. Okay, so actually one other thing that I can update while we wait here. I had to make a change to the system. You'll notice that none of the low voltage numbers are showing. You might have noticed this already. So one of the problems I was having is that I was using certain devices to measure the low voltage, voltage, current, and power of each individual circuit. And this was a way to kind of tell if the circuit's actually activating. And it was also a way that I wanted to kind of also measure all of the power of the system that's being used. So even on the control circuits, not just the things like the heating element or the filtration system. And I was using a chip called an INA 219. Again, this is pretty technical, but what these chips do is they have their own capabilities inside of them to measure voltage, current, and power. Then they transmit that out into something else like my Mega that I'm using to run the whole system. And they do that through a protocol called SDA-SCL, which again is pretty technical. But the advantage is that you can have a lot of these devices on one trace on your circuit board, and it just goes into the same 2 pins on the Mega. So you don't have to have like 20 pins and 20 different traces, lines on the circuit board. You can just have 2, and it can do all of them. That's the thinking anyway. Well, my problem was that I had too many circuits, and I couldn't keep all of the devices on at the same time. And not only that, but I was running into some other problems too because of just the physics and the nature of the hardware. My traces were really long, and I was turning, as I was turning them on and off to measure, what it was doing was it was actually causing my program to hang, to stop at certain times. And it was kind of random. And that was because of all the noise and everything that was going on with my system. Sometimes if the signal didn't get sent right, my program would just freeze, and then it would, have to basically reset itself and recover. And obviously that's not what you want to happen you could be brewing for a couple of hours. So like you don't want to get halfway through and then this system causes your program to freeze, and then maybe some of your data gets lost, maybe your controls get screwed up. So anyway, what I decided to do was just totally disable that. And since I did that, the system works flawlessly now. There's no delays, there's no hiccups. So while I'm losing some data, it's not going to be huge because number one, those power values are actually pretty low. They're not pulling a lot of power. The sensors are not pulling a lot of power. The things that are going to be like your valves, the pump is going to pull maybe a couple of amps. But those are pretty, short things, and I can account for that later because I know the voltage and I know the current draw, so I can manually add that back in later, at least until I come up with a more robust fix for the system. So I had to do that. I made the call. I didn't want to because I hate losing out on that data, but at the end of the day, the system performs so much better without it. And you can see the heating element is using like 1.3 kilowatts. That is vastly more power than all of these combined are going to use. So at the end of the day, it's okay to approximate the lower voltage stuff because that power is going to, be so much more insignificant than what the heating element and the filtration system is going to be doing. So just wanted to mention that because you might have noticed that those numbers aren't updating anymore, and that's why I had to make that change. But at the end of the day, it was needed because the system just performs so much more better without that. because of the nature of those chips. And you know, these lessons learned, I would totally do it differently, you know, now, now that I know this stuff. So lessons learned, and you know, we'll improve it in the next iteration somewhere down the road. So, okay, so what we're seeing now is we're getting pretty close. You know, we're within a couple of degrees here. The heater is, you know, barely running. It's at 36%. Of a duty cycle, so it's just kind of now, you know, slowly creeping up to towards the set point. And again, the idea is to get there quickly but not overshoot it, and you just want to kind of maintain that. That's the most important thing. So in another second here, we're getting pretty close. I think what I'll do now is I'll go ahead and turn the pump on, and then we'll go out and take a look at the system. So now we've got everything running, heater's running, temperature sensor. So this is exactly what the condition is going to be when it's mashing. Specific gravity, heating element, temperature sensor, and then the pump running. So I'll pause it here. We'll go outside and take a look at what the system's actually doing. Okay, so here we are outside now, and a couple things are going on. You can hear a couple of things. So first of all, the water is circulating. You can probably hear that. We'll go ahead and take a peek in here. See, water's coming in. That's good. I've got kind of just a manual temperature gauge there as a check, so you can see we're pretty close to our 75 set point. Pump's working. I'll show you if you can hear that. There's another thing that maybe you can hear, which is the actual sound of the buzzer as it goes up in frequency, and that's the cycle. So I'm going to go ahead and be quiet here and see if you can hear it. Okay, so hopefully you could hear that. I'm not sure, I'll have to check, but essentially what that is what you're hearing is the actual buzzer making the vibrations. It's producing a sound, but it is doing the vibrations. Obviously you're not going to be able to see it. It's not a lot of power. It's very, very small, and the frequencies are very large. So I mean, we're talking, I think it's 5,000 to 8,000 hertz is what we're doing. So pretty high frequency stuff. It's not like you're going to actually see it. So that's what that's doing. So now the system's just, you know, totally working here. Yeah. So if the nice thing is I was able to kind of also reuse some of the hardware of the system. So when the heater turns on, that light actually, the button there actually works on off, and it lights up when the heater's on. So it's like it's another nice just like visual check. The system is doing what it should be doing. Okay, so I just want to take another quick few seconds here just to show what the dashboard's doing. So out there, you know, you maybe saw from the temperature gauge we were right about 75.3, and that's what our system's actually telling us. So that's good, a good kind of manual check just to make sure that's working. The other thing here is that our frequency is shifted already. So now you see we've stabilized at around 5,700 hertz. And so what that's reflecting is now we're running other things. We're running a pump. You've got fluid actually moving through the tube. So it's already changing the characteristics of what the system was doing at steady state. The nice thing is that it's consistent. So it's a consistent shift. That's telling us that the system is actually doing what it should. It's reacting to the natural, you know, response of the system. And the actual value is not so important to us, so it doesn't matter that it's changed. What will matter is how it changes as the mashing goes on. So whether it's, you know, 6,400 or 5,700, that's insignificant. But what matters is once we actually are mashing and starting to brew beer, you know, it's at 5,700. Now how does it change from that level? And that's what we'll use. So it's that delta that we'll use eventually to correlate to how the specific gravity changes. So just something interesting there. And what we can do is I'll go ahead and shut this off. And then what I'll do is, well, I want to take just a quick look at the data that gets produced. So we'll go ahead and pause for a second. I'll bring up the database. Okay, so here we are now in the database viewer that I'm using. Again, this is a SQLite database, so if you're interested in that kind of thing. A couple things. So number one, I have 2 sessions in here. That was from some old data, so we'll have to watch for that. So now we'll go to sensor data, and we'll have to go to session 2, session ID 2 to start seeing, there we go, the most recent data here. Okay, so it's right around here. You can see how we started at around 51 degrees. And that kind of stabilized, didn't do anything. Now we turned on the specific gravity sensor, and that slowly came up. Target temp updated somewhere along the line here. Now we're at 75, steady. And so essentially what this is just going to show, it's time stamped, so we'll be able to track all this over time, which is the most important thing. If you go over to the high voltage section here, you'll be able to see, again, there's 2 sessions, so it's logging the high voltage power, and this is when it's cycling on and off. So you'll see bursts of power and then off. So that's all updating great. So the data is being recorded correctly. I'll have to make a few adjustments for some of these things, like to manually add in the low voltage information. I'm probably going to update the code to add in, so instead of tracking low voltage information, since I'm not doing that anymore, I'll probably just add in a simple indicator, like what circuit was on, when it was on, so we can start to see when was the pump turned on. That'll probably be valuable. So I'll look at doing that. But yeah, so I mean, you can see here it's pretty consistent, and then it locks in at around 5700 until we turn it off. So that's good. Data looks good. Everything looks good. We'll go ahead and wrap up the video. Okay, so that's it for this video. Kind of a long one, but it had a lot of key updates and changes since the last one. So the most exciting thing is now, we're at a point where we can actually start to brew the beer, which is the exciting stuff. And then what we'll do is we'll get into, kind of analyzing the data and showing the final result, showing the beer that was brewed and all of that. So thanks for sticking with me on this one, and I'll see you in the next one.